Okay, in this video, we're going to continue our discussion of hypothesis testing, and we're going to work through a one-sided test. So here is our question. Via Rail recently installed new passing tracks on a centralized traffic control system on the line between Kingston and Ottawa in order to reduce delays. Suppose that before the improvements, trains between Kingston and Ottawa were on average 12.4 minutes late. After the improvements, a consumer group monitored delays during a period of 3 months. For a random sample of 35 trains, it found that the average delay to be 6.2 minutes with a standard deviation of 8 minutes. The improvements reduced by half, they claimed. So then the question asks us the following questions. Have average delays been reduced? State your hypothesis and calculate a p-value. State any assumptions you're making and whether or not they're likely to be true. And then we're asked to calculate a 95% confidence interval for the delays after improvements, assuming the conditions are satisfied. Comment on the validity of your confidence interval. Okay, so let's go ahead and work through this question. So first, let's go ahead and check our assumptions and conditions. So one of the things that we're going to check is, or at least we're going to assume, since it says state our assumptions, we're going to assume that the trains are independent of each other. We are going to assume that, we don't even have to assume. We're told that there's a random sample. We're told that there's a random sample, so random. So independent, yes. Random, yes. We are going to look and say, well, is 10% less, is it less than 10% of the population? So less than 10% of population. And given our sample size is 35, I think it's safe to say that more than 350 trains run between Kingston and Ottawa, so we're going to say yes as well. So we now need to go ahead and look at, if we're assuming some kind of relatively normal distribution, we notice that what's missing from the question is that we don't have a population standard deviation and we have a relatively low or small sample size. So we're going to go ahead and use our t distribution. But before we get there, let's go ahead and write our hypotheses. So in this case, our H naught, or our null hypothesis, is simply saying that the average delay, we'll put a colon there instead, that the average delay, or mu, is equal to 12.4 minutes. Right? This was the average delay before the improvements. Our alternative hypothesis, or HA, so alternative hypothesis, is simply that mu is less than 12.4 minutes. Right? Why is it simply less than and not does not equal? Well, in this case, the question is asking us, have the average delays been reduced, meaning less than 12.4 minutes? So we are interested in a one-sided test here. So less than is our one-sided test. So there we can write down a few other pieces of information. So our sample size, our value of n, is equal to 35 trains. We have a sample mean, or y bar, of equal to 6.2 minutes. 6.2 minutes. and we're told that we have a standard deviation of 8 minutes. So standard deviation of y bar is equal to 8 minutes. So now we can go ahead and create our t-test. So our t is equal to y bar minus our expected value divided by the standard error of y bar. Well, we recall that the standard error of y bar is simply equal to the standard deviation of y bar divided by the square root of n. So therefore, 8 divided by the square root of 35 is equal to 8 divided by the square root of 35 is equal to 1.3522. And we'll just put it to 4 decimal points. So back to our t-score. So t is equal to, well, our y bar was equal to 6.2 minus 12.4 divided by 1.3522. So 6.2 minus 12.4 gives us negative 6.2 divided by 1.3522, which gives us a t-score of negative 4.5851. And we'll just say that this is equal to negative 4.59. Now, let's remember what our t-distribution looks like. So our t-distribution looks very similar to our normal distribution. The biggest difference being that we have a little bit more room in our tails. That's down here. So we got a t-score of negative 4.59. And we want to know if there is a level of statistical significance. So let's go ahead and look to our t-test or our t-table, and we'll remember that our degrees of freedom is simply equal to n minus 1. So this is equal to 35 minus 1, which is equal to 34. So we're going to look up our critical t-value at 34 degrees of freedom. So when we're looking at our t-table, we have to remember that what we are working with is a one-tailed test. And we are looking for our 95% level or an alpha of 0.05. So what we're looking for is an area to the left of 0.05. Since we're dealing with a one-tailed test, still with an alpha of 0.05. So then we go and look at our table, and we notice that there isn't 34 degrees of freedom. So to save ourselves a little bit of work, what we're going to do is we're going to round down to our nearest level. So we're going to look here at 30, and I believe that should do it. Yep. So our critical t value is 1.697. Now, importantly, it's symmetrical, so this could be negative 1.697. And this is our value for t star. So importantly, then, what we conclude is since t is less than t star, we know that the probability that y bar is less than, we'll just say this. We'll just say the following. Since t is less than t star, we know that the probability is less than 0.05. Therefore, there is a statistically significant difference and we would reject the null hypothesis in favor of the alternative. So there's some nuances to this question that we could ask ourselves, such that could we really use a t-distribution? Because when we're working with delays, theoretically, you can never have a negative delay. You could theoretically say you're arriving ahead of schedule, so it's possible. But we'd want to give careful consideration to whether or not we could assume a t-distribution or not. If you can assume a t-distribution, then we can say that we would reject the null hypothesis in favor of the alternative, given our level of statistical significance. But if not, you wouldn't be able to make that conclusion. Okay, so now that we've done A, let's go to B. So B, calculate the 95% confidence interval for the delay. So we remember that our confidence interval is simply equal to our estimate plus or minus our margin of error, where our estimate plus or minus our t star at n minus 1 degrees of freedom times our standard error of y bar, right? So we have our estimate of 6.2. So 6.2 is our estimate, plus or minus our critical value. So our critical t value, if we were to go ahead and look this up in our table, in this case, where before we were using a one-sided test, now we're going to go back to our two-sided test since we're going to have plus or minus. So we're going to look right here. So 0.05 in our two tails. We're looking for 34 degrees of freedom. Of course, that is not on our table, so we could use computation to find the exact value of 34 degrees of freedom, or interpolation if we wanted, or we could just use this estimate here. And it's a conservative estimate, so 2.042. So let's just go ahead and use that value. So 2.042. And again, if your professor wants you to use interpolation, you should use interpolation, but it's not always necessary. Times our standard error, and just as a reminder, our standard error is equal to our standard deviation divided by the square root of our sample size. So we get 6.2 plus or minus 2.042 times our standard error, which was 1.3522. So we get 6.2 plus or minus 2.042 times 1.3522 plus or minus 2.7612. So 6.2 minus 2.7612 gives us 3.4388. And 6.2 plus 2.7612 gives us 8.9612. So this would be our 95% confidence interval of the lateness of the train. So again, we can put this on a number line if we wanted to. We can set this as time 0. And what we're looking at then is a 95% confidence interval that the train is somewhere between 3.4388 minutes late and 8.9612 minutes late. We notice that that initial estimate that we had of, 12.4. If we say that this is all in minutes, we notice that initial estimate of 12.4 is not in our 95% confidence interval, supporting what we concluded using our t-test which was that it was less than 0.05. So therefore, it supports our conclusion. That's it for this video, but if you found that it helped make statistics easy, consider showing your support by giving the video a like. And if you still need more help with statistics, then consider subscribing to the channel if you haven't already. I look forward to solving many more problems with you next time.